Hello, this is the 5-minute lightning talk for the paper, Local Expectation Testing for Terraform, by Zach Gleason, Srinadish Chinmayan Ilayam, and Yaroslav Busko. In this paper, we explore potential solutions for testing Terraform, an infrastructure as code library, locally, using AWS-mocking tools LocalStack and Moto. Specifically, this paper proposes a framework for testing Terraform configurations that can 1. Identify errors locally that were previously only detectable in the cloud, 2. Speed up test runtime, and 3. Save money. Currently, there is no comprehensive local testing solution for Terraform. Hashicorp, the company behind Terraform, provides a testing framework to guide users through 4 stages of testing: unit test, contract test, integration test, and end-to-end test. However, only unit tests and contract tests are local, and they are used to primarily test the functionality of Terraform built-in functions or your input and output formatting. In our research, we also uncovered multiple other tools for item potency checking, code smell, and other quality metrics. However, none of them provide the high-fidelity local tests that we are striving for in this paper. In our experiments, we used the tools Moto and LocalStack. Moto is a mock AWS service used primarily as a Python module in place of Boto. In our case, we were able to use it as a standalone server to connect to. LocalStack is a fully functioning local AWS cloud environment that supports many of the services on AWS, including the ones that we were testing: EC2, SNS, S3, and DynamoDB. It is run within a Docker container. Both of these tools are only available on AWS. In our experimentation, we expected the following behavior. If a test fails locally, it should not pass remotely. We don't want our tests to introduce any new errors that don't already exist within the infrastructure stack. Second, if a test passes locally, it most likely passes remotely. There are some limitations, such as EC2 instance type, that would be impossible to catch a bad type locally. Last, there are no cloud resources created. For a test to be local, it cannot create any resources in AWS. We created a total of 10 test cases across 4 AWS services: EC2, SNS, S3, and DynamoDB. In our experiment, we created a Terraform error and tested that error locally on Moto and LocalStack and in AWS. We fixed the error and again tested on Moto, LocalStack, and AWS. We record the accuracy, time, and cost during the runs. We then repeated this 10 times to account for outliers, such as network errors or AWS downtime. On this slide, we see the accuracy results from our experiments where we are testing if Moto and LocalStack are consistent with AWS in failing and passing Terraform runs. As shown in the success column, Moto and LocalStack match AWS in passing every test. In the failure column, we see Moto and LocalStack match AWS in throwing an error on almost every test case. These results match our expected behavior because every test that threw an error locally also threw an error on AWS. Further, most tests that passed locally also passed on AWS, with the exceptions being EC2 create instance of bad type and EC2 create instance with bad AMI on LocalStack and Moto, and DynamoDB create table with hyphen in name on Moto. On this slide, we see our time results where we create a heat map to quickly understand insights from the data. As we can see, the average failure of AWS timing was consistently longer than the average failure of LocalStack or Moto timing. Similarly, the average success AWS timing was consistently longer than the average success timing of LocalStack and Moto. Here, we show the costs of our experiments on AWS in the failure test cases and the success test cases. We don't show the LocalStack or Moto testing costs because there is no cost for the local creation of resources. Similarly, there is no creation cost in AWS where the error occurs before any resources are created. As we can see, the cost is very small. Overall, we believe our results were promising as they showed high accuracy and time savings across most tests. The cost savings were low in our unit tests, but applied to corporate tech stacks, our framework could provide meaningful savings. In the future, we would like to expand our work by supporting more clouds, adding more tests, and applying our framework to corporate infrastructure stacks. All resources can be found at this GitHub link, and if you have any follow-up questions, you can contact us at the listed email addresses.